Yeah. طيب, بسم الله الرحمن الرحيم. We'll continue talking about the IP address, and today we are going to discuss the first topic, which how we distribute the IP addresses amongst the different networks. As we have discussed before, leveraging the hierarchical architecture of the internet, what happens is that the IP addresses get assigned to the service providers based on their size or their scale. So tier one service providers, they get like very wide range of IP addresses, which in turn can be divided into sub ranges to tier 2 and tier 3 and so on. So that's the main message in here. So tier 1, as we have discussed before, it focuses on large national or international internet service providers, which commonly provide this service to tier 2 and tier 3 service providers, in addition to, of course, individual users, if they choose to do that. So they offer, of course, high reliability and very high bandwidth and very high speed links, like fiber optics links and so on and so forth. So they have huge infrastructure that they offer as a service to tier 2 and tier 3 providers. And then, of course, tier 2, they get chunk of this, and then again tier 3 get chunk of this. So an important tool to do that is that we have like a big range of IP addresses, and then we need to do what we call subnetting. We need to do subdivisions of this wide range of IP addresses into subdivisions which can be assigned to service providers, and this can be done recursively, okay, all the way until we assign this to individual users. Another important aspect of IP addresses is that there are some special IP address ranges. These IP addresses are agreed upon to be used for a particular purpose. It's not for general purpose. So for example, the default route is one of the special IP addresses in a network, although the default route does not have a specific IP address. It takes any IP address. Usually it takes the first host address in the network. So if your network is, for example, 192.168.1.0, this is your network, then 1 will be the default route. Usually that's how it's assigned. However, it does not have a fixed IP address. Unlike loopback address is a special address which takes any IP address in this range. So this whole range is allocated to loopback. So from 127.0.0.1 all the way to 255. And this loopback is used, for example, to test your TCP/IP card. So you send something and then you receive it back. So on the same machine. So whenever you do like ping on 127, so you receive the ping back on the machine. So if you receive something, this means that your card is working fine. Okay, so there's nothing wrong with the card. So it's used for troubleshooting. So if the loopback works, but the ping to a remote host doesn't work, then the problem is not in your local machine. The problem is in the network itself, in the switch or in the router or in the final host that you're trying to ping to, something like that. But it's not in your local host. So loopback is an address that indicates the local host. So you send something to yourself, and when you try to receive it, then you make sure that the protocols and the hardware of the card are working fine. Link local addresses. These link local addresses, they get assigned by the operating system automatically in case you do not have any dynamic IP address configuration in the network. What happens is that, as we said before, when the computer first starts, the first thing it does is that it allocates a dynamic IP address, right? By connecting to what? To the DHCP, right? So what happens if the DHCP is down or there's something wrong with the DHCP and you cannot get to it? So in that case, the operating system will assign to you an IP address in that range. So if you are working on your machine at any point in time, and then you find that the IP address dynamically assigned to your machine is in that range, then you figure out that DHCP is not working fine, or you lost the connection to the DHCP. So the operating system or the workstation was not able to connect to DHCP. Of course, using this IP address, you cannot access the internet. So it's an indication to you that any communication to the internet will not probably work, right? So you can probably communicate locally, but you cannot communicate to the internet. So this testnet IP addresses, these addresses are used for education and testing purposes. So whenever you are implementing a protocol for the first time, like proprietary protocol or something, and then you want to test this protocol with a real equipment or on a real network, then when you can use some of these IP addresses. And these are usually also used for documentation, so for education purposes in general. For documentation, if you want to explain in a document or in an RFC, for example, you want to explain a specific example about a network and how you configure it and stuff, then this range is used. One of the most important ranges of IP address is what we call the private IP address. So we're going to talk about that as part of the network address translation, which probably you have talked about before. So the private IP address has a local significance inside a specific network, but it has no significance or no meaning for the service provider. The service provider should never receive any packet or a frame with an IP address in these ranges. So this private IP address is used as we said, the main rule of thumb for IP address is that, if you remember in the early lectures we talked about, we said that the IP address is unique for a specific host across the internet. This concept of private IP address breaks that rule. So potentially you can actually use these private IP address on local networks and you can reuse it. So this host, for example, may have the same private IP address like this host or like this host. Okay? So ideally, the IP address should be unique. So this host should not have the same IP address like this host. However, using this private IP address concept, because the IP address has local significance within the boundaries of these networks, once any packet goes out from this network, it should never have any IP address in this range. and therefore, the ISP blocks any packets with any IP address in these ranges, because these are private, these are not public. So once you go outside your network, you have to use the public IP address, which is any IP address that's not in these three ranges. So the first range is any host address in that range from 10.0.0.0 all the way to 10.255. And these are agreed upon ranges. Okay, it's not that it has any specific reason why they choose this, but these are ranges that have been agreed upon. The 172.16, and when I say 16, I mean like 0, 0, 0, 0, 0, 1, and all zeros, right? So, which means that all these 4 bits can vary to form anything from 16 all the way to a la 1 and 4 zeros all the way to 1, 1, 1, 1, 1. What is this number? This is 31. Okay, so all the network addresses and IP addresses in this range can be a private IP address. This this is a range that uses non-natural boundary. Okay. So the subnet mask of this is a/e. حدود /12. برافو عليك. /12. يبقى 8, the first 8 bits for this byte, and then 4 bits from this byte. So it's /12. Okay. And this one, which is which breaks at the natural boundary, it's 192.168. This is the most famous. This is what we use in our houses. This is the default range that's used by many of the routers that we use in our houses. Okay. So again, this is a private IP address. So at home, so we can use these private IP addresses freely, but what we probably didn't know before is that the packets that we send to the internet, they do not actually have these addresses. Otherwise, it's not. I mean, it doesn't have it doesn't fulfill the main rule of IP address, which is the uniqueness. It has to be unique, right?
So, Doctor, now every house it has a network that accommodates 2 to the power 16.
Right. Yeah. So actually, and you can actually use this range if you like, which gives you 2 to the power 24. Yeah. Yeah. Right. So in each house.
You can have 2 to the power 16 devices.
Right, but these are reusable or recycled IP addresses. These are not consuming from the range, and that's one of the tricks that they use to mitigate the shortage of IP. Right? Yeah. Because the shortage of IP is based on the fact that you have to have a unique IP. But using the private address, it doesn't have to be unique. But you need something extra to work with your router in order to facilitate the usage of these private IP addresses and show it to the world that this is actually a unique IP address, even though it's not unique.
So if the device wants to access the network, the internet, it will use the IP address for the router?
Right, yes. We're going to talk about this. So we need what we call network address translation or port address translation to translate or to map from the private IP address to the public IP address. So what happens is that Ooredoo gives you only one IP. In some cases, maybe 2, but you probably don't know the other IP. But anyway, you get an IP address, depending on your plan. And you don't need any more IPs. You just need one IP address. So any traffic that goes out from your network, it gets mapped to your public IP address. So each individual user, like a house, gets only one IP address. So inside the house, you can use the private IPs. Go ahead.
Can I know the IP address of the house?
Yes. From your router configuration.
Can I know it, for example, from IP config
On the host, no. You have to connect to the router itself.
Can I connect to the router through my device?
Yes, of course.
How?
Using the admin user interface. Usually, it's again, if you go through the default route, 192.168.1.1, then you get to the. But you do it on the browser. Yes, so that links you to the router admin interface. So from the admin interface, you go to TCP/IP configuration. You get the.
So I write the.
It's not a secret, yeah.
It's the IP. I take the IP of the router
Right.
then I put it in the browser,
Right.
and then I get the admin access.
Yeah, that's assuming that you know the user ID and password for the admin. Usually it's admin, but sometimes they change it. Okay. So
When you call them, they give it to you.
yeah, they give it to you. It's not a secret, yeah. If you break it down, it's your problem. So in any way, these private IP addresses, they get blocked completely by the ISP. So the ISP should never receive these IP addresses by any chance. Which means that it allows all the way to like 16 million, theoretically, which is 2 to the power 24 host addresses on one single network. So ideally, they actually, this range is particularly for large organizations that requires this range of IP address. But usually large organizations they get not a single IP in that case. They get a range of IP, in which case they subdivide this into subnets, and then they assign different IPs to different subnets. And if needed, then they can use the private IP inside the subnet itself, if needed. But anyway, using the NAT, so using the private IP requires that you need to have NAT activated in your router. Otherwise, it will not work. So for example, if the university decides to use any private IP in any of the labs, then they need to run or activate NAT in the router that's connected with this. So otherwise, it will not work. Okay. So the network address translation is the mechanism that facilitates the recycling or the reusability of these private IP addresses on multiple networks all at the same time. So what happens is that inside your network, you can use 192.168.anything. Okay. Any packets that goes to the router is layer 3, right? So it has access to the IP header. So what it does is that it replaces the IP address header, the IP address in the header, with your public IP address before it gets out. So for every single packet, it has to do that. Okay? And not only that, we'll see one more thing that it has to do. That's the reason for this is to mitigate or to try to avoid the shortage of IP address version 4, right? Because we said that the ranges are really congested, and the only way for us to do that is to break the rule of uniqueness of the IP and make it reusable. So this way we can. This is one of the main reasons that IP version 4 did not die until today, even though we have billions of devices, but still IP version 4 is still surviving until now. But people are realizing more and more is that it's not gonna live another like maybe 20 years or something. It has to sunset at some point. So this is the main idea. So if the router here has NAT, what it does is that for any call from this host, for example, this host has a source address of 10.0.0.3, which is one of the private addresses. So what happens is that the router receives this, and the router will consult or will put an entry in the NAT table, and this NAT table has what? Has the private IP, the public IP, and the destination IP address where this code needs to go to. So this host is trying to call or to do, like, for example, telnet or FTP to this remote server on the internet. So the router will then say, okay, I will put this entry in the table to map 10.0.0.3 to the public IP address of that router, okay, which is 179. This is not in the private range. .9.8.80. This is the IP address that you get from the service provider. Okay? And the outside global IP address, which is again not a private IP address. It should never be a private IP address. Okay? Which is 128.23.2.2. Okay? So why does it do that? Well, it needs to put this entry to map, because for each call to the server, there's probably a feedback or a reply, right? So when the reply comes back, I need to map back from the public IP address to the private IP address in order to send it to the host. Okay, so it's very simple idea. Okay, so this mapping is it's an overhead. Right? It's an overhead. So for every single packet that goes through the router has to do that. Takes the private IP, put the public IP, send it. When the reply comes back, take the public IP, put the private IP, send it. Okay, it's an overhead, but this is the only way we can get around the shortage of IP. Okay, so that's a simple example. But so the question here is that, well, on the network, I mean, the main reason for using the private IP is to use multiple IPs or for multiple hosts on the same network and use the same public IP, right? Otherwise, there's no point of using the one single public IP address. If we have only one host on the network, then we can assign this public IP directly to the host, and that's it. But typically, what we have is multiple routers. So this example talks about the fact that we have two hosts on the local network. Both of them, they want to connect to the same remote server, which is likely to happen. Okay, so you want to connect from two different machines to one FTP server or to Google or whatever. Okay, so that's very likely to happen. So if we use the exact same concept, then 10.0.0.2 will be replaced by 172.9.8.80, and will go to this remote IP address. And 10.0.0.3, okay, will be replaced with the same thing. So you will end up with two packets like this. One will be replaced with the 10.0.0.3 will be replaced by this, and the other one will be replaced by the same IP address with the same remote, and then the two packets will go out. Right? So the problem happens when you return back the replies for these two packets. So the router will then have to map back from this public IP to this or to this. Right? So how do we do that? It's a simple database rule. It's a many-to-one relationship.
Yeah.
So many-to-one is not a reversible direction. So if you have many entities that are combined into one entity, then from this entity you cannot know which one it came from. So on the way back, you cannot map it to one of these two. You will not be able to distinguish between the two. So the only way you can use NAT, or the only way for NAT to work, is that if you have one call at a time, which means that you end up with one address only, or one entry in the NAT table. That's it. And that's not possible because, it's you cannot accommodate the fact that you have only one entry, or one host will be able to do one request and one reply at one single time. You cannot do that. So to resolve this issue, we need to have, we need to return it back to one-to-one relationship, not many-to-one, right? So we need to have a one-to-one relationship. So the only way for us to do that is by using another piece of information in addition to this host address to indicate that this is coming from that. So if we add this piece of information together with the IP, then on the way back we have one common IP, but we have another piece of information that tells us which host originated that request. Okay, so we need another piece of information to do that. And guess what is the other piece of information? Port. So, so what we could do is that we can use the, so in that case, remember, in that case, NAT, or in that case, PAT, has access to both IP header and transport layer header, which elevates the router to have to work in the transport layer to be able to perform PAT. Okay, it has to do that. So that's an exception to the fact that we said that router in general is a network layer device. However, using PAT, it actually has to access the transport layer header as well, because the port numbers do not exist in the network layer header. So if you have a packet that has a destination address like this, source address like this, and assume that this server is an HTTP server, so I want to call the HTTP server, and this is the source port. Okay, so we have to use port numbers as well to facilitate this one-to-one relationship. So what we will do is that the PAT, the port address translation, in the router will map this to the same destination address, the same destination port, so nothing changed here. And then the source port, the source address, will change to the public IP, right? And then we have the source port, which dynamically assigned by the PAT service on the router, to distinguish that this is actually coming from this host. So if this host tries to do the same thing, this host now tries to send this packet, then what will happen is that I will replace it with the exact same destination address. Source address will be the same. So until here, both of them are the same, right? But the main difference will be here in the port number. That's why it's called port address translation. So this will have the call from this port, and this will have the call from this port. And guess what? Now the port will have to represent two pieces of information. Which application on which host requested this? So the port number will temporarily play two roles in that case, right? It will no longer indicate only the application on the same host. It will indicate this application on this host that originated this packet, right? So it will have two purposes now, okay? Which is okay, because, I mean, chances are you would not run 2 to the power 16 different applications on one single machine. So the only limitation here is that on your entire network, you will not be able to run more than 2 to the power 16 different applications globally on your home network, which is, again, I mean, it's reasonable. Okay. But this is the drawback, or this is the price that you have to pay in order to facilitate the usage of private IP addresses. So this way, on the way back, I have to use the path table. Now will have the private IP, the public IP, the remote host, and the source port and the public source port. So on the way back, when you receive this packet, using this address and the source port, you will be able to return back to this host and this port.
Even the source port is different in the public.
It has to be.
In the private.
Yes, it has to be. It has to be different for each application on each host that originates this packet. Which means that if the same host tries to generate a packet from a different application, then this port will be different and this port will be different.
Why?
This is the only way you can generate this one-to-one relationship, because now I know that 3333 is actually mapped back to 10.0.0.3 and not 10.0.0.2. Because 10.0.0.2 generated this port number, which is 4 2s. It doesn't use 4 3s. So this way I can have the mapping back from both the public IP and the port. I can go back to here or here. So this is the only way for me to create this one-to-one relationship. Okay?
Doctor, I could have, even in this account, the source port 1331, right?
Yes, the source port here is 1331.
Yeah, we could have the other one the same. That's why you have to change it here, right?
Here, yes, here we could have the source port. Maybe it was assigned by the operating system by chance to be 1331. That's a good point.
So that's why you have to change it.
In that case, this one will be different from this as well.
Yes.
So even if the source ports here are the same, these source ports will have to be different to indicate the fact that this is coming from this IP and this is coming from this IP. Okay? So any questions? So this is on the way back. So on the way back, here the path service inside the router will have to do the reverse operation. We'll have to map from, of course, on the way back, of course, the destination IP will be the public IP of this port, right? And the source IP will be the source IP address of the server. The destination IP will be the same destination, the destination port will be the same source port that we used in the previous slide. And the source port will be the source port of the HTTP service. So in that case, we know we have to use both the destination port and the destination address. We have to use both. And then we'll map those two into those two. Even if the destination port is the same, but here the destination port is different. If the private destination ports are the same, but the public destination ports have to be different. Okay? So this way I can have this one-to-one relationship. So now the concept of subnetting is another very important tool that usually it's used by tier 1 and tier 2 service providers in order to subnet the network or the range of IP into smaller ranges that can be assigned to different service providers or to different users, and then routers will be able to route from one subnet to another. So the subnet, the concept of subnetting has several advantages. I cannot use one network as one entity horizontally and use all the IP addresses all at once. The subnetting will allow me to have subnetworks and then route between these networks as appropriate. So this is more practical rather than having one single flat network with number of hosts that's like 2 to the power 24. You cannot have like one single network with this number of hosts. It's not scalable and it doesn't make any sense. So you need to break down this huge network into subnetworks and be able to route and control the traffic that goes from one subnet to another. So this way you can have more granularity on how to control the different subnets and how to manage the traffic that goes back and forth between these subnets. But there is a price that you have to pay, really. So subnetting as a concept talks about the process of borrowing bits from the host bits. So ideally, we have this is the network part and this is the host part. But as a service provider, I decided to borrow from the host part some subnets, which allows me to break down into subnetworks. Breaking down into subnetworks is more practical, as I said, to make your network more manageable and more controllable. But subnetting doesn't give you more hosts. It's not, unlike NAT and PAT, which is used to mitigate the shortage of IP, this one actually, it makes you lose IPs.
Yes. For the address and...
because for each subnet now you have to designate a network subnet address and broadcast for this particular subnet. So instead of having one network and one broadcast for the entire range or for the entire network, now you have to break it down into subnets and have one broadcast and one network address for each subnet, which is a price that you have to pay for subnetting. So this is an example. So if we have a network which is 172.16.0.0, then we want to subnet this network. The one simple way is to say, okay, I will borrow the whole byte, the whole third byte, to indicate the subnet. So this is what we call the subnet number. So 0, 1, 2, 3, all the way to 255. This is the subnet number. For subnet, it's usually okay to use 255, by the way. Okay, it's not typical to use 255 on the first byte. But for subnets, it's okay. You can use 255 as part of the subnet address. Okay? So, and then you use this third byte for subnet address, and they use the fourth byte for host. So now, the IP address is divided into 3 parts. And luckily, we will not divide it more than that. So it's not worth dividing it more than 3 parts. So we divide it into the network part, the subnet part, and the host part. So this way, I can break down my network into smaller subnetworks with reasonable number of hosts, and I can manage these subnetworks with good level of control. So for each subnetwork then, one subnetwork is 172.16.0. And what is the subnet mask for this subnetwork? It's a /24. So now from a /16 network, I will break it down into a 255 or 256 actually different subnets, each subnet with a 254 or /24 subnets. Okay, so this way I can have up to 256 subnetworks. Each one will have this number. 254 host addresses that start from 1 all the way to 254. The subnet address will be .0.0 or .1.0 or .2.0 and so on. And the broadcast will have a 255. Okay? Most of the exercises about chapter 6 will be in that category. Will be just to take a network, subnet it into different subnets, and then be able to deal with the subnet mask, the host ranges, and what is the subnetwork address, and so on. Of course, so one common exercise could be, I will borrow only like 4 bits of the third byte, or 5 bits. So the subnet mask in that case will end at the non-natural boundaries, and then you should be able to calculate the subnetwork address and subnetwork mask, of course, and the host ranges for each one. Okay. اوكي احنا ملتزمين باليوم. هو ده الميقات الوحيد بالنسبه لي. At least I started at 10 on this watch, so I stopped it. Okay, so I will talk about this example and then we'll break. So this is the host IP address. A host like this, which has the IP address 172.16.3.0/24. So if I decide to use no subnetting, so I need to. So in that case, this network has 172.16.0.0. This is /16. Okay. So from this, if we use no subnetting, I can break it down into 256 subnets using this number. But without subnetting, the host range will range from 0.1 all the way to 255.254, which gives me 2 to the power 16 minus 2 different hosts. So this exact same example can be broken into subnets, 256 subnets, each with 2 to the power 8 minus 2 hosts times the 256. So, so the first subnet will have the subnet address of 172.16.0.0, and the first host will be 172.16.0.1 all the way to 255 on that byte, and each of these networks will have a /24 subnet. Okay. So this way, I lost how many host addresses in that case? How many host addresses I lost?
55 times 2, 16. 8 minus 4, 2 times 30 is 2 times 6.
256 times 2. 256
times 2.
256 times 2. These are the amount of host addresses I lost in that case. Minus 2, because even without subnetting you have to lose 2, right?
Yes.
So without subnetting you lose 2. With subnetting you lose 256 times 2, right? So it's 2. So because for each network you lost 2, and you have 256 networks, right? Right? So you have 256 networks times 2 minus 2. So this is the amount of host addresses that you will lose, if you break down the /16 network into /24 network like this. It's a significant number. It's not minus 2 because even without subnetting you lose 2 addresses, right? This is the amount of host addresses you lose due to subnetting. Due to subnetting. So without subnetting, you will lose 2. After you do subnetting, you lose 256 times 2, right? So due to subnetting, you have to subtract 2, which is in the case without subnetting. We're trying to get the number of host addresses that we lose if we were to use subnetting.